Please, Alberto, if you want to introduce the session and the first speaker.
Okay, welcome everybody to this section number 61, entitled Internal and External Determinants of Male Reproductive Health. Before starting, I would like to introduce ourselves. He's the actual SIG Andrology Coordinator. It's Dr. Francesco Lotti from Italy, and it's a pleasure for me to chair this session with him. And I am Alberto Pacheco from Spain. I am the next coordinator of SIG Andrology Group. So it's a pleasure to be here. And we have, during the session, we have five very interesting presentations focused on how different environmental factors can influence male factors, spermatogenesis, or sperm production. So let's start with the first presentation. The first speaker is Albert Salas Huetos from Spain, from Barcelona, and he is talking about associations between healthy and unhealthy dietary patterns and testicular function, a comprehensive analysis of individual food groups.
Before starting, just to say that Albert is the new senior deputy of SIG Andrology, so we have a new player in this World Cup, and so you have 3 of 6 SIG Andrology members here. So please, Albert.
So thank you, Francesco. Thank you, Alberto. First of all, I would like to thank the scientific committee for selecting our abstract as an oral presentation. I have no conflicts of interest, and as all of you know, male infertility has emerged as a growing public health concern over the recent decades, mainly driven by some different papers from Levine and collaborators that he's going to speak after me, suggesting a progressive decline in sperm quality parameters globally, basically in sperm count. Pointing out, of course, that modifiable factors could be the main cause of this global trend, and unhealthy diets are increasingly recognized as one of these important modifiable factors. The existing literature has largely examined nutrients and foods in isolation. Some examples of foods that are related with sperm quality parameters are veggies, fruits, nuts, and fish as beneficial foods, but others, like processed meat and red meat and ultra-processed food, as categorized as harmful foods. In parallel, nutrition science has shifted from studying isolating single nutrients or foods to focusing on dietary patterns, because they believe that these dietary patterns can capture synergistic interactions, but also reflect real-world eating behaviors. There is, in the last 3-4 years, a growing body of literature examining the associations between dietary patterns and testicular function. In general, the higher adherence to a Mediterranean diet and healthy plant-based diet are positively associated with aminogram parameters, but also higher adherence to the Western-style diet and healthy plant-based diets or diets high in ultra-processed food are inversely associated with aminogram parameters. However, no prior studies have comprehensively assessed the contribution of individual food groups within those dietary patterns. So the study question is really simple. Are dietary patterns more strongly associated with semen quality parameters than individual food groups in young men unselected for fertility status? In other words, this statement also makes sense in reproductive science. To do this, we analyzed a cross-sectional study, including young Danish men unselected for fertility status. The main exposure is basically men's diet. We analyzed with a PCA, we did a PCA to derive the a posteriori dietary patterns, but also we extract the primary contributing food groups from the two main dietary patterns. That means food groups with factor loadings more than 40. The main outcome of this study are basically semen quality parameters. This study includes 3,790 men with on that men we have food frequency questionnaire data. All of that men are non-azoospermic and with complete semen sample. Basically, as a statistical analysis, we did some analysis, but the main analysis is a multivariable adjusted linear regression models to estimate the associations between dietary patterns or food groups consumption in quartiles and the semen quality parameters. We, of course, adjust by several confoundings like age, BMI, history of reproductive diseases, physical activity, etc. Here you have the demographic and reproductive characteristics of the population. Basically, as I said, this population is really young. We have a median age of 19 years old. Those participants has highly educated mothers, and we have a median of 2.5 days of abstinence. And here you can see also the median of all the other sperm quality parameters. The first set of results examine the semen quality parameters according to dietary patterns. With the PCA, we identify 4 main dietary patterns. The first pattern, or the Western pattern, or also the unhealthy pattern. The pattern 2, or the prudent pattern, or the healthy pattern. And also a pattern 3 that we call open sandwich, and a pattern 4 that we call vegetarian-like pattern. Basically, you can see here the adjusted median differences in these semen quality parameters according those 4 dietary patterns consumption, and consistently and quite strong, we can see inversely associations between the adherence of a Western-style pattern and semen volume, but also total sperm count. To the contrary, with the prudent or the healthy dietary pattern, we found positive associations between the adherence of this healthy pattern and semen volume, sperm concentration, sperm count, but also progressive motility. After that, we did a PCA plot with the main 2-factor loadings, that means the unhealthy and the healthy pattern, with the objective to select the main possible food groups that contribute the most to that dietary patterns. And in red, you can see here the unhealthy foods, and in green, you have here the healthy foods that can explain the most those dietary patterns. So after that, we did multivariate adjusted linear regression models with those foods. In relation to semen volume, you can see here that we have some consistency with the previous data on the Western and the prudent pattern. So we can see an inverse association between French fries consumption or warm processed meat consumption and semen volume, but also with the healthy foods, we can see a positive association between veggie salad consumption and semen volume. These results in sperm concentration are not that consistent, and here you can see that only we found an inverse association between the consumption of pizza and sperm concentration. And we found nothing in those healthy food items. In sperm count, we found positive associations between vegetable salad and sperm count, that this is consistent with the prudent pattern results, and nothing, it appears, in total motility or progressive motility when we consider these isolated food items. In normal morphology, we only found an inverse association between the consumption of snacks and the normal sperm morphology, that it is nothing when we explore that patterns. So, of course, this study has some limitations. The cross-sectional study, the cross-sectional design precludes causal inference. The study population is very homogeneous, comprised young Danish men. We cannot exclude residual confounding, despite the comprehensive covariate adjustment, and only one semen sample was obtained per individual. So in conclusion, the results suggest that dietary patterns have stronger and more consistent associations with semen quality parameters than individual food groups, suggesting a synergistic interactions between nutrients and foods as we hypothesized previously, with vegetable salad showing the most consistent positive association and pizza, French fries, processed meat, and snacks being associated with poorer semen parameters. The findings support dietary pattern-based approaches rather than interventions targeting individual food groups or nutrients for optimizing testicular function. And I'm really proud to say that we received randomized clinical trial funding, that it's called the MedFertile, with the objective to explore the effect of a Mediterranean diet intervention on testicular function and potential mechanisms implicated in the changes. So I will try my best to prove that Mediterranean diet can be a good intervention in relation to testicular function. And of course, I would like to thank all the funding, people, and institutions that helped me to be here today, and to all of you for your attention.
So thank you very much. I would like, as usual, you are the first, so to have a question for you. So you know that Ludwig Feuerbach used to say that the man is what he eats or she eats. So this is very important. You showed that better food is important for semen parameters. But my question is, if we have any data about the prevalence of infertility, considering only natural pregnancy and not IVF, comparing, for example, United States and Mediterranean countries such as Spain, Italy, or Greece, even if semen parameters, so we should demonstrate it, and I think it's possible with the registries of Denmark, and it could be a good idea to develop together, to see if really the semen parameters in United States are lower than in Mediterranean countries, and what about infertility? So which is the clinical effect of this? So if there is more infertility couples or not? Do you know any data of this? I don't think so.
Really, I don't know. I don't have any data about this, or not that I know. But we can say that, of course, we are eating really different between countries, but of course, in Europe and United States for sure. I suppose it's not the only lifestyle factors that affects sperm quality or other reproductive outcomes, but I think it's really important lifestyle factors that has to be considered.
Because, you know, we used to say United States has 20 to 30% of obesity. Italy has 10. They eat with a diet that is worse. So you should expect lower semen parameters compared to lower prevalence of pregnancy and of born children. I'm not sure. So we should check even the outcomes, and I propose this to work together between Spain, Denmark, and me, and we can check.
Yeah, sure. Do you know that there is some publications showing that the people that adheres the most to Mediterranean diet patterns are not Mediterranean diet countries, are not Mediterranean countries. There are a lot of adherents of a Mediterranean diet in the north part of Europe. So it should be interesting also to see what happened with those countries.
Thank you.
We have a question on the left.
Ghulam Lahad, UK. The global population decline is in the salad-eating intellectual people. It's not in the burgers and chips-eating population. I just want to see your reaction. That's all there is.
Okay, thanks.
Okay. I think we have
Short question. Only one short question. Answer.
You say you say at the end you recommend diet advice based on diet patterns rather than specific food groups. How does that then flip with the meaning smart and measurable objective people to focus on? I mean, if you tell me eat healthier, it's difficult. If you say cut out bread, I'll cut out meat, I'll cut out sandwiches, I'll cut out load of things would be advantageous.
I can hear you.
So you say that you are advising dietary advice based on patterns and not specific food groups. How does that connect with the need for smart and measurable objectives to focus on? If you tell me eat healthier, it's difficult. If you say cut out bread, I'm going to cut out sandwiches, I'm going to cut out tea, I'm going to cut out tea, I'm going to cut out whole grain foods. The focusing on a specific food helps enforce the pattern.
So I think it's better now to focus on dietary patterns than foods, and at the same time it's better to talk about foods than nutrients, because we cannot say that we are eating nutrients, but also we are not eating only foods. So my perspective or my suggestion is to go and shift to dietary patterns that can explain better that modifications in the sperm parameters. For example, it's better to talk about Mediterranean diet than go to restrict your diet on ultra-processed food, for example.
Okay. Sorry.
Really quick, 30 seconds, because I think it's really important. It's showed now that intermittent fasting, especially in men, has an increased effect on overall health, from cardiac health all the way to sperm motility and mobility. Have you considered including that into your research, intermittent fasting, alongside with, let's say, I don't know, Mediterranean diet or other diets?
Yeah, it's interesting, that point, yeah. We are not on that point right now, but yeah, it should be interesting to research. Yeah.
Okay.
Thanks.
Okay, thank you very much.
Thank you very much. So we have to move on with Dr. Hagai Levine with the lecture on temporal trends in total and free testosterone from 1972 to 2019, a systematic review and meta-trend analysis. Please.
Thank you, Francisco. I'm really delighted to present to you for the first time our new systematic review and meta-analysis on trends in testosterone. We are the same group that previously published the meta-analysis on sperm count. Who around here think that there is a global decline in sperm count? Raise your hand, please, if you think that there is a global decline in sperm count. We don't know what is the situation about testosterone. That's what we try to answer in this study. We have no conflict of interest to declare, and I must say that I had the privilege to work with outstanding scientists on this study, and especially Alon Levy, my student who led the study under my supervision. So when we speak about testosterone, very briefly, as we know, it's a key hormone for not only masculinization, but also for general health and also for reproductive health, for spermatogenesis. We know from recent studies that impaired total testosterone hereafter TT is associated with increased mortality. So, of course, complex associations, it could be a marker, but still we know that testosterone is very important. When we measure testosterone, we know it's complicated because it's regulated by luteinizing hormone, hereafter LH, and sex hormone binding globulin, SHBG. So we are actually interested in the free testosterone, hereafter FT, which represent the biologically active testosterone. However, we have measurement issues with that. We also know that testosterone is affected by measurement in the time of the day, by age, by obesity, and also by some other factors. And you can see here David, the statue of David the King, representing that mankind was interested in masculinity for many centuries. So this is our previous study. I will not go over it, but I just want to note that beside what we think is a relatively strong evidence, and there's also evidence from other groups for the decline in sperm concentration, we see some kind of acceleration after the year 2000. So that's another interesting note. And others have noted, and you can see here the study by Skakebeck and others, about the testicular dysgenesis syndrome and disruption of the development of the testis. I do want to know that testosterone is crucial here because, as you can see, testosterone, decreased testosterone production is crucial as a pathway mechanism and also crucial as an outcome that later also impact reduced fecundity. So testosterone is of special importance. In this study, we took the best practices approach. We used the Moose, Prisma, and pre-registered in Prospero. What we did is a new method. We are the group that did the sperm count meta-analysis, that we took all the available data with the same measurement, hemocytometer, and tried to see the trends. Here, because testosterone measurements vary so much between laboratories and also because of the differences between populations, we took a different approach, what we called trend studies. We looked for studies of testosterone that studied trend, that took a similar population, exactly the same methods, the same researchers, look again at the same population, try to assess trends over time. We thought that would be a good way to understand trends. So our inclusion criteria was that testosterone was measured at least twice over more than 2 or more years in similar unbiased population, of course not a population of people with infertility problem, etc. And our outcomes were the slope, the trends of total testosterone, TT, calculated free testosterone, the CFT, using the Vermeulen formula, SHBG and LH, but I will not go back to LH because we simply did not have enough data for that. We did for each study, for each trend study, we did a random effect meta-analysis by pulling age-stratified annual change, meaning that in the same study, there were different age groups. So we looked at the trend in each of the age group, and then by meta-analysis methods, grouped them together to get the slope for a single study. And later, we did a meta-analysis, a random effect, which is the more conservative way, random effect meta-analysis to combine all the studies together. Overall, although we started with nearly 10,000 papers that we screened, we ended up with only 12 studies that were included in the systematic review and only 6 studies that were included in the meta-analysis, and I will refer to it. Obviously, it's a major limitation. So, beware and behold, that's the main result. And as you can see here, and I will later show the 6 studies, what happened in each of the study, but in each study, we saw a clear decline in total testosterone. But when we add up by a random effect model, we see a clear, significant decline by minus 0.26 nanomole per liter per year. And if we look over the entire period of time, 1972 to 2019, we see over 50% decline, 54.6% decline overall in the model of the 6 studies. And you can see here the 6 different studies. Again, in each of the study, and we didn't look for decline studies, we looked for trend studies. If there were any studies that testosterone is stabilizing or increasing, we would love to put it in the meta-analysis, but we didn't find such studies. We only found, so far, studies that show a trend of decline, and the 6 studies are from different countries, somewhat different populations. We well adjusted for the age. We were not able to adjust for obesity because of the lack of the relevant data in the studies. We did contact the authors to get the original database to try to model as best as possible, and we were able to do it for some of the studies. When we split the studies before 2000 and after 2000, you see it's 3 studies and 3 studies. That's all. Please notice that the scale is different, so it looks rather similar, but it's not similar. The trend for the 3 studies pre-2000, the decline was minus 0.17 with a confidence interval of minus 0.3 to 0.05, so a significant clear decline, but the magnitude for the post-2000 studies was doubled, was minus 0.33 nanomole per liter per year, which with confidence interval, much narrow confidence interval of minus 0.35 to minus 0.31. So there is a suggestion here for acceleration of the decline. Again, only 3 studies and 3 studies, but this is interesting to note. We also looked for calculated free testosterone, which again is very important because it reflects the available testosterone as far as we can tell. And here again, we see a clear decline for the 3 studies. The 3 of them show the decline, but the first one, as you can see, Anderson, it was not as significant statistically. But when we look overall, you look at the random effect model, you see a summary of minus 4.13 picomole per liter per year, and the confidence interval minus 8.17 to minus 0.008. So it's close to cross 0, but it is significant. So again, I must say I'm here. I'm very glad to be here at ESHRE. I call upon all of us to do more studies on testosterone trends, so at least in the future we will have better data, but to the best available data, we see a decline in both total testosterone and calculated free testosterone. We also saw some hint of decline for SHBG, but it was not statistically significant. So if we discuss, and I must say, and I don't know if there is anyone here in the room from the Santi group, they recently published a meta-analysis on testosterone trends, and they did a very good work in collecting all the available data. They took the cross-sectional approach, similar to our sperm count studies. They looked and found rather similar decline in total testosterone, and they have much more data, and also a decline in luteinizing hormone, in LH. So I think that the 2 studies, in some extent, complement each other, and I think that we now have better evidence for total testosterone and maybe also free testosterone decline. As I said, the study is mainly limited by the sample size, and also we are limited by our inability to adjust for obesity. Obviously, obesity and maybe diet as well. Obesity contributed to this decline, but I do not know by how much. It's hard to believe, despite the dramatic increase in obesity, that, and we'll try to model it, that it will explain fully the decline. There are probably additional causes for the decline. The entire process was transparent according to the protocol done by 2 reviewers, etc. And the fact that we looked at several outcomes, I think, strengthened the study. The implications, I'm here to discuss it with you. I will gladly, during this session, and afterwards I will stay here to discuss with you the implications of the study. It was still did not publish in the literature. It's the first time that I present it. But I think that together with the other adverse reproductive health trends that we see, we have a very clear wake-up call here. We need to pay more attention. I'm also the chairman of the Israel Association of Public Health. We need to pay more attention globally to male reproductive health. We issued the Stockholm Statement 8 years ago, and I still think that we know too little about what is going on with reproduction of men globally and what are the causes that are driving it. Nevertheless, we already know many of the factors, both in utero exposure and later on in adult life, that harm male reproductive health, and we already need to take actions to reverse them, including environmental exposure, including climate change, including unhealthy lifestyle habits such as poor diet and lack of physical activity, etc. And again, I'm very grateful for ESHRE to be able to present it. I don't know what would happen to David the King nowadays with the decline in testosterone and with the obesity epidemic. You can see what the AI think about it. Other than that, there was no use for AI in this presentation. And here is my email. I would love to hear your thoughts and to collaborate with you. And again, I want to thank not only the chairs, but the entire ESHRE for this wonderful organization of the conference. Thank you very much.
Okay, now open for discussion. Any question in the audience? Yes, on the left.
Yes, I'm here. Hello.
I can.
My name is Blombeck Jensen from Denmark. Thank you for a very interesting talk. I have 2 small questions for you. So your meta-analysis showed a declining in semen quality, and now you also have a very small one showing a declining total testosterone and calculated free testosterone. I think it's worth mentioning that some of your collaborators did a 20-year-long prospective study on semen quality in young Danish men, where they followed them annually for 20 years and found no decline in sperm concentration over that 20-year period. That could be worth mentioning, especially when you come out with testosterone, because if there was a big declining testosterone, why not measure it in these young, where it's controlled over a 20-year period, and then see if there is a decline there? Have you done that in these young men that were followed for 20 years?
Yeah, it's a bit hard to hear for some reason, but I think that I got your point. And the question is that we have conflicting evidence from other specific studies, and you mentioned about the sperm concentration. First, I mean, here we focus on the testosterone, so with the brevity of time, I will not go into that specifically. But I think the main issue that we have a clue here, even if there is, 5% chance that this is true, and there is a 50% decline in testosterone, surely we need to do something about it. So I do agree, we need more cohort studies, we need more animal studies, more laboratory studies, we need more epidemiological studies to understand the trends. Unfortunately, we don't, as an epidemiologist, I'm saying, we don't integrate enough in regular cohorts the measurement of testosterone, the measurement of semen quality. I think that would be a great addition, and then we could much better understand not only the trends, but also the causes and the interaction with other health indicators. Thank you.
And the second thing is, when you see the declining total testosterone, as an endocrinologist, this decline is mainly a reflection of the increase in BMI you may have seen in the same period of time. So it would be very interesting to see your changes in serum level of luteinizing hormone. Because if it's a real hypogonadism, you would see an increase in luteinizing hormone, and my guess would be that you also see a drop in luteinizing hormone in these patients.
I agree, and I think that if you can look at the Santi paper, which to some extent complement this, but again, I think we need all of us to create more data in order to answer these important questions and to know what is the contribution of obesity.
Hi, George Halak from Brazil. Nice presentation. If you look at the data have you looked at the data post-COVID? That would be interesting. We have published like 18 papers on COVID, and the virus destroys Leydig cells, and the whole test is affected by the COVID, the SARS-CoV-2. And we've seen that the patients, they do recover testosterone levels, but at the expense of high LH. So there is some kind of testicular dysfunction after COVID. It would be nice if you complement your data after COVID. Maybe we could do some things together. And also we look at the Amazon, some population, the Amazon rainforest, 400 families in the remote areas of the Amazon. Those people, I mean, they don't have the erectile dysfunction, their hormones are okay, and they have kids until late age. So it may be also related to the environmental and economical and like healthy pollution, etc. So maybe
so please, short question, and no, because we have to move on.
If you look in the 60 studies, where they are from, which cities they are, polluted cities, how is the lifestyle of the population? Maybe there are other factors than just declining testosterone, maybe social events or pollution, air pollution, etc.
Definitely, just want to note that, thanks for the question, obviously not in this study because it ended in 2019, but we know that not only endocrine disrupting chemicals, but also stress is a very serious endocrine disruptor. And I think that to study more the impact of stress on male reproductive health and on testosterone, including during pandemics, during wars, as unfortunately we witnessed in the Middle East, etc., this is very important area to further explore.
Yeah. Okay. So thank you. Anyway, I agree, as endocrinologists, it should be nice to see even the same data for LH. Because if it's obesity, we have functional hypogonadism. If it's other things like testicular damage, we will see something different. So let's see. Sure. Thank you very much.
Okay, let's move on to the next speaker. Next speaker is Carrie Nobles, and title of his presentation is Internal and External Determinants of, exposure of air pollution mixtures during spermatogenesis and sperm DNA methylation in men seeking infertility treatment. Sorry, thank you.
Great, yeah, thank you so much. So I'm delighted to be here to present our work. And to start, I have no conflicts of interest to declare. So spermatogenesis is estimated to last about 74 days and encompasses the developmental process from germ cell division all the way through production of sperm capable of fertilization. So this includes early cell division windows of mitosis and meiosis, as well as morphologic development during spermiogenesis. And developing sperm are uniquely susceptible to redox stress, other harmful factors in circulation, as well as targeting by the immune system. And the blood-testis barrier plays an important role in protecting developing sperm. And our work is looking at sperm epigenetics and specifically sperm DNA methylation. And it's thought that sperm DNA methylation signatures may be largely established during these early cell division windows of mitosis and meiosis, and this may be a particularly important exposure window. So air pollution is associated with systemic increases in inflammation and redox stress. And this may be associated with dysregulation of the blood-testis barrier and increased exposure of sperm to redox stress and to immune factors. And there's a robust body of evidence suggesting that air pollution is associated with decrements in semen quality, including sperm count, motility, and morphology. However, the mechanisms underlying this and how they might translate to fertility and also downstream to pregnancy and offspring health is less understood. And there are a few smaller studies that have suggested air pollution may impact sperm DNA methylation. So in our study, we asked the question whether air pollution exposure across developmental windows of spermatogenesis may be associated with changes in sperm DNA methylation. So we did this leveraging secondary data from the folic acid and zinc supplementation trial. This trial enrolled over 2,000 men from study sites near Salt Lake City, Utah, who are part of a couple seeking infertility treatment, and they provided 4 semen samples at 2-month intervals, and sperm DNA methylation was previously measured, and the sample provided 6 months after enrollment. So participants in the study were predominantly from moderate to high-income households and non-Hispanic white, and we also have a mixture of men both with and without male factor infertility. So we added estimates of air pollution using the community multi-scale air quality model. So this is a photochemical transport model that estimates daily air pollution for 12 by 12 kilometer grid cells. And we linked men to the grid cell that contained their geocoded residential address. And one of the challenges of looking at air pollution is that air pollution is a mixture. So what we're exposed to very much depends on where we live. And this can make attributing exposure to specific air pollutants quite challenging. So, and I'll present in a minute, so we evaluated mixtures in our study. And for this, we incorporated data on nitrogen dioxide, ozone, and fine particulate matter, and additionally looked at the 6 major constituents of PM2.5 in those mixture models. So sperm DNA methylation was measured in 60% of participants who provided a 6-month semen sample, and was measured using the Illumina methylation epic bead chip array, which measures over 800,000 CpG sites. Pre-processing was done in MinFi and Combat, and we corrected for genomic inflation using Bacon. To be able to link air pollution exposure to methylation of CpG sites, we estimated exposure windows based on timing of the semen sample. So this included a window for the 74 days before the sample for spermatogenesis, as well as windows for specific developmental processes that were estimated based on the literature for mitosis, meiosis, spermiogenesis, and spermiation. For our analysis, we used a 2-step approach. And the first step, we conducted an epigenome-wide association study using a traditional multi-pollutant model, which co-adjusted for PM2.5, ozone, and nitrogen dioxide, and adjusted for additional covariates. And here we abstracted all CpGs that were associated with 1 or more air pollutants at a p-value less than 0.0001. In our second step, we analyzed these CpGs using a mixture approach called quantile G computation. So this is a method that estimates a weighted mixture of pollutants, and then in regression looks at the effect of increasing exposure to all of those pollutants jointly by a quantile. So rather than looking at an individual pollutant effect, here we're looking at a mixture effect. And for both of our analyses, none of the associations survived correction for the false discovery rate. So we applied p-values, 2 thresholds, one of 0.0001 and one of 0.005. So for our main findings, so of the over 800,000 CpG sites we initially screened, there were 797 CpGs that were associated with 1 or more air pollutants at our threshold. And then for our mixture model analyses, the mixture was associated with 10 CpGs annotated to 8 genes at our lowest threshold, and an additional 34 CpGs annotated to 28 genes at our higher threshold. And so the Venn diagram to the right shows the timing of exposure in relation to those CpG sites. We're seeing a little bit of overlap, but associations with exposure across spermatogenesis, and then specifically for mitosis and meiosis, and also later for spermiation at the end of spermatogenesis. And I'm going to walk through, so for many of these genes, were already associated with spermatogenesis in the literature or functions important for spermatogenesis. So I'm going to walk through some of those genetic functions that we observed. So first, we observed the majority of associations with genes associated with stem cell population maintenance and differentiation of spermatozoa. And you can see here, so we're seeing associations for many of these across the entire window of spermatogenesis in blue, but also here for most of these genes with associations early in spermatogenesis during mitosis and meiosis, although not for every single gene. And along the bottom, so the major pollutants indicates the pollutants that contributed the greatest to that individual mixture model. And we're generally seeing ozone and nitrogen dioxide being the strongest contributors. And so these genes were observing roles in stem cell maintenance, differentiation, and Sertoli cell function. And we're also observing a trend of both hypermethylation of some genes and hypomethylation of other genes. We additionally observed genes associated with microtubule organization and chromosome segregation, including genes specifically associated with dynamics related to Sertoli cell function and blood testis barrier function. And here also seeing a little bit more of an exposure with earlier during spermatogenesis. And then we observed genes associated with RNA processing and regulation and with translation. And interestingly here, a little bit more of an association later in spermatogenesis. But again, with genes that either implicated in spermatogenesis or in some cases homologs to genes that are testes specific. And then we also observed genes associated with the endosomal lysosomal system or phagocytosis as well. Now these genes were a little less specifically associated with spermatogenesis in the literature, but may be important in response to air pollution exposure. And finally, we found an association with guanine nucleotide binding protein. So this is an imprinted gene that broadly plays a role in regulating hormone and neurotransmitter signaling and is associated with men's infertility, low sperm motility, and poor embryo development. And you'll note we found the strongest association with exposure late in spermatogenesis during the window of spermiation. And this is consistent with some findings from the literature suggesting that guanine nucleotide binding protein may play a role in acrosome formation, shedding of cytoplasm, and in sperm acquiring motility. So in summary, we observed that air pollution mixtures may be associated with differential methylation of genes involved in stem cell maintenance, differentiation of spermatozoa, chromosomal organization, and proteostasis. We looked at an overall mixture effect. However, for our mixture, we observed ozone and nitrogen dioxide to be the strongest contributors, but that may vary based on location for a study population. So there are several limitations that are important to take into account for a study. So a big one is a large number of comparisons that we looked at, increasing our risk of type 1 error. So we did use low p-value thresholds to try to isolate those pollutants that are most strongly associated, and our findings were consistent with genetic functions that have been observed in prior research. However, further replication of our findings in other cohorts is absolutely critical. So in conclusion, exposure to air pollution is ubiquitous. It's something we're all exposed to, and something with a lot of recent upcoming challenges, including climate change, may undo some of the gains we've made in this area. So this remains a really important area of research. Our findings do support prior research suggesting men's air pollution exposure may impact some of these key regulatory processes during spermatogenesis. In addition to replicating findings, it's important for future research to understand how some of these changes may be associated with downstream impacts on infertility and potentially for pregnancy and offspring health. And with that, I'd like to thank my co-authors for all their contributions to this project, and also a special thank you to the FAST researchers, staff, and study participants, and to my funder. And I'm happy to take any questions.
So, short questions and short answers.
No worries, Francesco. Very short question here. Thanks so much, Carrie, for your really interesting talk. You mentioned that 60% of the participants had the DNA methylation tested. Just wondering, was there a clinical reason for that, and what are the risks of potential selection effects and selection bias in your sample? Because you've got really great causal inference thinking throughout, so I imagine you might have looked at this.
Yeah, that's a great question. So the 60% I think was due to the men who actually came in to provide the semen sample, so it's part of the study. However, we have looked at characteristics for men who did and did not provide a sample, relatively similar. We've also, and a lot of work, actually not for the mixtures, but some of our additional earlier work in here, used inverse probability weighting for factors that were associated with selection, and don't see much of a difference for that too. But I think a really important point.
Hi, I just have a really quick question. Thank you so much for your talk. I think a lot of studies have shown that lower income is typically placed, like lower income housing is typically placed near high air pollution areas. Have you considered stratifying your data by income for more like applicable public health output?
Yeah, I think wonderful question. Completely agree. We do see inequities in air pollution that definitely a trend with other social inequities as well. So we have, for some of these analyses, tried to adjust for things like area level deprivation index to see if there are any changes, and also like self-report of household incomes and factors like that. We don't see too much difference, but I think one limitation is we have a pretty broad measure for air pollution of a 12 by 12 kilometer grid cell, so that may limit our ability to disentangle some of that, but an excellent point.
Thank you very much. Okay, let's move on to the next speaker. Next speaker is Rocío Núñez Calonge from Spain, and the title of his presentation is Does Male Lifestyle Influence Geographical Differences in Semen Quality? Thank you, Rocío.
Thank you, Chairman, Co-Chairman, and thank you for being here. Thank you also, Scientific Committee, for accepting this work. I have no any conflict of interest. I forget to introduce the slide. As well, the previous speakers showed that there is a decline in number of sperm, the quality of sperm in the population. There is a growing consensus regarding the existence of geographical differences in semen quality. And one of the first papers published in this topic in 1996 suggests that these differences in this geographical differences in semen quality could represent an important bias in studies of semen quality. And since then, several papers have subsequently been published in different regions worldwide, in Europe, in the States, in China. And for example, in Spain, this paper was published in 2008, reporting significant differences among a population of sperm donors. However, this paper, as well as others on this field, have several limitations. For example, semen analyses were performed in different laboratories, often with non-standardized methodologies, and focusing on a population of young people. So our group carried out this study published 2 years ago, evaluating semen quality across 12 different regions in Spain, and confirming the existence of these geographical differences in our country. As you see here in this table, here are the total number of motile sperm. The best place with a higher number of total motile sperm was in North Spain, specifically in Asturias, and the lower number was in South Spain. And you see here also the total number of motile sperm with all the regions included in this study, with significant differences between them. Nevertheless, unfortunately, the information regarding some confounding factors, such as body mass index, cigarette smoking, alcohol, etc., was not available in this study, and therefore the influence of lifestyle in these semen parameters could not be assessed. So we decided to expand this study, and the objective was to determine whether geographical differences in semen quality remain significant after adjusting for male lifestyle and socio-demographic factors. This is a prospective study involving 7 centers located in different geographical regions of Spain. Here you are in the map, the participants in the study. Between June 2024 and December 2025. And a total of 442 men undergoing fertility evaluation were included. And the semen analysis included semen volume, sperm concentration, motility, morphology, and total motile sperm count. And all the analyses were performed with the same methodology and all centers belonging to the same center. And all participants completed a health and lifestyle questionnaire, included the place of residence, body mass index, medical history, allergies, physical activity, chemical exposure, medication, if they are smokers, number of cigarettes smoked per day, alcohol consumption, recreational drug use, coffee intake, and previous day of sexual abstinence. And the results were correlated with semen parameters. Of the 442 patients initially included in the study, were excluded 14 azoospermie patients, 7 cannabis users, 1 cocaine user, and 32 patients who lives out of the place of residence or included in this study. So finally, 386 subjects were included in the analysis. And the participants were divided into 4 groups, depending on the place of residence, the northern, southern, central, and southeast of Spain. And here you are the distribution of the patient in each region. Here you are the methodology, the statistics that we use for the univariate analysis and the multivariate analysis, and we obtain the following results. First of all, in the univariate analysis, we found statistical significant differences among the 4 regions included in the study in volume, concentration, motility, morphology, total motile sperm count, and the proportion of men with asteno and teratozoospermia. And you see here in the graph that, for example, concentration and motility are higher in the North Spain, in green, whereas the morphology was better in southeast of Spain. And the total motile sperm count was also higher in North Spain. And the proportion of patients with oligozoospermia and astenozoospermia was lower also in North Spain. When the 4 areas, the geographical areas, were compared considering all the confounding factors that we included in the study, we found significant differences only for the previous abstinence, the coffee intake, and the proportion of men living in capital. Interestingly, among all the confounding factors analyzed, only the abstinence, the previous abstinence, was correlated with semen parameters. In the multivariate analysis, you see here also statistical significant differences among the 4 regions included in the study, with the higher motility and morphology in North Spain. And in this table, we can find that previous abstinence and geographical location remain independently associated with semen parameters after adjustment with all confounders, with all cofactors. And total motile sperm count was independently associated with both abstinence and geographical location, and the proportion of astenozoospermia patients and teratozoospermia patients was correlated with semen parameters. So, in conclusion, our findings confirmed that the geographical differences in semen quality previously described in Spain persist independently of lifestyle and sociodemographic factors, even after adjustment for potential confounders. Sperm concentration and motility were clearly higher in North Spain, whereas sperm morphology showed better results in southeastern region compared with the other geographical areas studied. Only abstinence duration independently influenced semen volume, concentration, and morphology. However, it did not affect the prevalence of oligo, asteno, or teratospermia diagnosis. To sum up, taking together, these findings suggest that other determinants potentiating environmental factors may contribute to regional differences in semen quality. But we should acknowledge several limitations. First, it was a clinical cohort rather than a population-based sample. Second, lifestyle information was self-reported and therefore subject to reporting bias. Third, direct environmental exposure measurements were not available. And finally, semen analysis was based on a single sample per participant, and the observational nature of this study precludes establishing causal relationships. And probably there are more limitations that are not included here. But finally, the final message could be that overall, our study strengthens the evidence supporting true geographical variation in semen quality in Spain and highlights the need for future research exploring environmental and regional determinants of male reproductive health. And of course, I would like to thank our team that supported this study. Thank you very much.
So I have a question. I am sure that all the centers that were joining the project were following WHO guidelines for semen evaluation, as well as external quality control. Maybe they are of the same group. But I would like to know if there was, before starting the study, a real inter-operator comparability evaluation to be sure that the difference was not related maybe to some. Because, you know, it is strange that sperm concentration is higher in the north, but morphology is higher in the south. Because usually sperm parameters, they go quite together. And when you have oligoastenoterato, it is always going in the same way. So,
yes, this is a very good question because I think it's very important that the parameters are standardized in all centers. And we have internal and external controls for all the parameters. I think that one of the less objective parameters are morphology. I totally trust in concentration and motility. I only have a very comfortable thinking about the morphology, but I think the morphology are less reliable than the other parameters, are more subjective than the other one. Even we did several control and to compare the results among all the centers. But I'm very confident with the results in this sense.
thank you.
We have a question,
Yes.
on the right.
Thank you. Mike Eisenberg, Stanford. This was great, I think very important work, because we do see, regional differences in our own country, the United States, for example, if you sample, around. And so I think certainly lifestyle exposures are different, but the other difference that we have is there could be different kind of regions of origin. Obviously, we're a country of immigrants, maybe despite current administration's acknowledgement, but I was curious if there are also differences in Spain as well about where these men originated.
Yes. For this, I showed that others papers show it in different countries, in China or in the States, the same results in different regions. Yes. Okay.
Okay, Rocío, only short question. Have you checked, because you found the most differences in cities than in big cities, have you checked for the stress in those populations? Because perhaps it could be one important factor affecting sperm quality.
Yes, this is one of the things
cortisol, some hormones.
Yes, for example, stress. we thought after the results, we saw the results, stress, pollution, because the two big cities compared with the different, almost double of the total sperm count was in the north, in center, and probably pollution, probably stress. And we think to test thereafter, because we think it could be a possibility. Thank you.
Thank you.
Thank you very much. So we move on to the last lecture from Dr. Joy Thibudi. Please. And the title of her lecture is Predictive Factors for Intrauterine Insemination Success, a 5-year analysis of more than 5,000 cycles and multivariable determinants.
Yeah. A very good afternoon, respected chairpersons, distinguished audience. So I'm Dr. Jyoti, I come from India. This work is by my doctor fellow, Adya, and I monitored it closely. It's a privilege to present our work in this platform, global platform, ESHRE. We all know reproductive medicine is a rapidly evolving field. IUI plays a very important role as a treatment across the globe. Especially in our country, coming from India, IUI is the most indispensable treatment because of its simplicity, accessibility, and cost effectiveness. Yet, there are questions to be answered. Couples sitting right in front of us, can we predict what is the success rate for them? Do we have a predictor module to tell the optimum success of IUI? Yes, exactly. Our study addresses this question. It's a large study of 5 years with 5,000 cycles, multivariable determinants of pregnancy outcome. So I have no conflict of interest. So the paradox of IUI, though it remains the most widely utilized treatment, it bridges the gap between the expected management and IVF. Yet, its success remains inherently difficult to predict. Now, what's the missing link? The missing link is the precision patient selection. The objective of our study is very simple. It is twofold. First, to calculate which is the independent predictor, whether the clinical, seminal, or procedural aspect, which increases the IUI outcome in a large 5 years cohort. And later, this could be integrated in an AI-based decision model, and then it becomes so simple for us to counsel the patient even before initiation of the treatment. Now, the methodology. One of the biggest strengths of our study is a scale. Over 5 years, 5,000 plus homologous IUI cycles across multiple 11 centers across India, analyzing using multivariable logistic regression. To our knowledge, this analysis is one of the largest for the population of our country. The inclusion criteria was simple, standard IUI inclusion criteria, which is women aged 21 to 45 years, men 23 to 55 years, and at least one patent fallopian tube, unexplained infertility, minimum to mild endometriosis, ovulatory dysfunction, and sperm analysis that count more than 10 million sperms. The exclusion criteria was women with bilateral tubal block or hydrosalpinx, moderate to severe endometriosis, any congenital uterine anomalies, untreated endocrine disorders, and the usage of donor sperms. The pathway was very simple. Since a standardized pathway was used across all our centers, the variables could be compared. The following pathway was used to minimize procedural variability. Ovulation induction was by the normal standard ovulation induction protocol for IUI with oral and injectables. Serial follicular monitoring was done to see the lead follicle and the endometrium. At the appropriate time when the lead follicle was mature, ovulation was triggered with HCG, standard sperm preparation was used before insemination, and adequate luteal phase support was given to the women. Now we come to the most important question. How successful was IUI in the real world? In our cohort, the overall clinical pregnancy rates was 13.8%, with clinical pregnancy strictly defined as ultrasound visualization of a gestational sac. The statistic analysis, all the parameters were tabulated in the Excel sheet and a standard software was used. The categorical data was used by chi-square test, and the continuous data was measured with mean plus or minus standard deviation of a normal distribution variables were analyzed using t-test. P-value of 0.05% was considered statistically significant. Moving on to the results, our analysis identified 4 positive predictors and 3 negative predictors of clinical pregnancy following IUI. Among all the variables studied, post-wash total motile sperm count emerged as one of the strongest independent predictors of success. As the post-wash total motile sperm count increased, the clinical pregnancy rate improved significantly from 8.4% to the lowest category to 17.5% to the highest category, that is more than 10 millions. The association was highly significant. P-value was less than 0.001. In addition, the odds ratio of 2.2 indicated that couple with a higher post-wash total motile sperm count had more than twice the odds of achieving a clinical pregnancy compared with those in the lowest category. The strongest semen predictor was post-wash total motile sperm count. Of course, the third was endometrial thickness. More than 8 mm, we saw 15.4% improvement in the pregnancy rates. Duration of infertility, less than 5 years, pregnancy rates was 15.5% with a significant p-values. And what about the negative predictors of clinical pregnancy? First, women aged more than 40 years had negative impact on the success of IUI. Male age as well, more than 40 years, had a negative impact. And also there was a sub-study done with a study where when DFI was more than 30%, they had a significant negative impact in the pregnancy rates. In a nutshell, predicting IUI success, the key determinants from a 5 years, 5,000 cycle study, positive predictor for success, first being total motile sperm count more than 10 millions, second, progressive motility more than 30%, endometrial thickness more than 8 mm, and duration of infertility less than 5 years. The negative predictors for success were age of couples more than 40 years and DFI more than 30%. So I apologize for this busy slide, but I will summarize. The key message is that our findings were well aligned with the current literature published in the reputed journals. Factors such as female age, total motile sperm count, endometrial thickness, ovarian response, and infertility duration have consistently been the predictors of IUI success. What adds to the strength of the study is its scale, a large real-world cohort from the Indian population where such data are relatively limited. In addition, most of the predictors identified in our models are available even before performing the IUI. This makes the model clinically relevant, allowing better patient counseling and treatment planning even before starting the treatment. So the discussion, quick 7 points. This study basically attempted to identify important IUI variables with regards to clinical pregnancy rates, and then later to integrate it in AI module with a predictor score to help counsel the couples. The first, as usual, modifiable lifestyle factors may significantly influence IUI outcome. Healthy BMI, smoking cessation, regular physical activities and favorable metabolic health. Second, age remains the strongest biological determinant of IUI outcome. Third, duration of infertility is an important marker of reproductive prognosis. Fourth, adequate ovarian response significantly enhances the pregnancy probability. Fifth, endometrial thickness remains a critical component of successful implantation. Sixth, post-wash total motile sperm count continues to be a clinically important predictor. 7, developing an integrated predictor along with AI models may further improve IUI utilization. Of course, this study comes with limitation as well. Since it's a retrospective multicentric design, there was some inherent selection bias. Potential inter-center variability was existing. Prospective external validation is necessary. Future implications. We can use all the scores to identify the couples who should proceed directly to IVF, thereby reducing the ineffective IUI cycles, emotional burden, and treatment cost. Predictor models to be created across different population and fertility setting. Development of a mobile risk calculator to provide real-term prediction of clinical pregnancy rate, even before insemination. And incorporation of all additional biomarkers like antral follicular count, AMH, and lifestyle factors for further improved predictive accuracy. The ultimate goal is to empowering clinicians to deliver the right treatment to the right couple at the right time through evidence, precision, and personalized care. Before I conclude, I would like to express my sincere gratitude to Dr. Adya and Dr. Suma for their invaluable guidance and support throughout this study. I am also deeply grateful to my entire team for their dedication and hard work. Finally, thank you all of you for a kind attention. I would be happy to take any questions. Thank you.
So, thank you very much for being here. Such a long flight. And I have a question. According to the criteria you found, so if you take a sample of people with more than 10 million mobile spermatozoa and age below 40 and so on, how is the prevalence of pregnancy and then maybe live birth, considering one cycle of IUI? So, I mean, if you take into considerations these parameters, did you have a higher prevalence of pregnancy than what reported in literature?
Yeah, so definitely the age matters a lot in our studies as well. Pregnancy rates after 40 years, we have seen the decline in the pregnancy rates, and the age matters. And also, if we see in our study, single pregnancy rates, this is a pregnancy rates, clinical pregnancy rates of the parameter, but of course we have that limitation of not doing for the limited group.
No, I understand, but I mean, when you say, which is the possibility to have a pregnancy with IVF, usually you say 25% for cycle. If you say about IUI, you say about 10-12% for cycle. If you take into consideration all the parameters you found that each one is predictive for a better IUI outcome, how is the prevalence of success for single cycle?
Yeah, single cycle, what we have found in the study, it's a very good question. Follicles, when we see two follicles, the pregnancy rate improves in a subset of people when the ovarian stimulation was used with gonadotrophins rather than the oral ovulagens, and whenever the age of the couples were less, and also the parameters where we have seen increase in pregnancy rate mostly is in the women's age. Younger the age group, the pregnancy was better.
Okay. But do you have a number?
Gulam Bahadur.
No, sorry.
Congratulations for
Sorry,
the large study.
sorry, just to finish. But do you have a number, like to say, instead of 12% using this criteria, IUI in couples, according to these parameters, is 15%? I don't know.
So because we actually in our exclusion criteria, we restricted the age, like percentage of people of more than 40 years were lesser.
Okay.
So we go for, age was the criteria where we have excluded.
Thank you.
Yeah.
Sorry.
You've unraveled a number of factors that will contribute to a positive pregnancy. I don't know whether you've seen poster number 3 from us. We're looking at over 35s. The paper is now published. Over 35 with IUI. We're matching the same results as IVF. Not only that, we have expanded the scope from not just unexplained infertility to include male factor infertility using consecutive ejaculate, because these are the easiest women to get pregnant. But within your study, you haven't told us some of the things like what stimulation cycles you're using, and secondly, number of follicles, because one of the things that we did identify was a second follicle will significantly increase.
Yeah, thank you so much by hearing the great...
the stimulation cycle.
Yeah, so the stimulation was standardized throughout all the centers. We call the women on the day 2 of the cycle. We do a basic scan. We rule out any follicular cyst, and we see the anti-follicular count. And then we start with the oral ovular gel. That is our standard for the first cycle. 3rd day to 5th day. And then we call her for a scan. When we see a lead follicle, then we don't add gonadotrophins. If we don't see a lead follicle, we add the gonadotrophins there. That is the protocol what we use. So most of the time it was, single follicle, and because of gonadotrophins, sometimes I've seen double follicles as well. This was the limitation of the study.
But I urge you to look at poster 3.
Yeah.
Okay, time is up, so we have time only for a very short question and
very short
also for
question.
answer.
I wanted to know how many, Jyoti, congratulations first. My name is Sonia, I'm from Pakistan. I just wanted to ask you, did you have any ectopic pregnancies? Because your selection criteria, you also included patients that had only one patent tube.
Yeah, so the ectopic pregnancy was not included for the clinical pregnancy rates, because we had, of course, ectopic pregnancies, but not very few. Our clinical pregnancy score was based on seeing a confirmed sac in the uterus.
Thank you.
Thank you.
Thank you very much. So we are very happy to tell you that I think this session was really very interesting, and it's time for coffee break. Thank you very much for being here.